Welcome to this Introduction to Energy Storage lesson. My name is Will White, Curriculum Developer and Instructor here at SEI, and I will be your presenter for this lesson. We are going to talk about the purposes of energy storage, and we're going to go through a list of some basic terminology that we need to understand when talking about battery storage systems. Let's take a look at this graph on the right-hand side of the screen. This shows 2 days worth of energy consumption. That's the purplish line. We can see that this is what's typical of a residential load. Consumption goes up in the morning, drops down a little bit during the day when most people are out of the house, and then peaks in the evening where everyone returns home, gets all their stuff done in the evening, and then goes to bed, and the cycle repeats itself on day 2. The PV line is quite different than the load line because the PV produces energy and power during the day. On day 1, we had a bright sunny day. This is very typical of a day with clear sun, no clouds, no shading on this system. Day 2 looks like it was a cloudy day. Maybe it was raining that day, although the intensity of the sunlight was pretty steady all day. We can see that nice curve, although it is quite a bit lower than the other curve. So why do we have energy storage? Well, we can use energy storage to store the excess generation during the day to use it later, like at night when our PV is not producing any power. With battery storage, we are storing that energy in a chemical form. We're using a chemical reaction to store that energy. And this is a reversible reaction. The reaction goes one way when we're charging and goes the opposite way when we are discharging. Again, we're using this storage to save our energy for times when the sun isn't shining, or if we had a wind system when the wind isn't blowing. We can also use this energy storage to support the utility grid through advanced functions, which are way beyond the scope of this lesson. Energy storage and batteries can be used in off-grid systems to provide power during a surge, to start certain equipment, typically ones that have a motor like a refrigerator or an air compressor or a well pump. These motors need a surge of power to get started, and then once they're spinning, the power demand goes down. So the battery storage can provide that power. We can also use it for voltage stabilization. This kind of goes in line with the grid support and the advanced functions. If we need to have power in a remote location, we can use small batteries and have portable power. We can charge the batteries up in a location where we have access to the grid or renewable energy and take that battery to the remote location and have power available to operate loads that we may need in that remote location. There are many different types of systems that integrate battery storage. There are many different applications. We can use them off-grid, we can use them on-grid, we can use them for backup power, we can use them for grid support, for other advanced functions. A lot of different ways that we use battery energy storage. Let's look at some of the terms that we use commonly when referring to batteries and designing systems with batteries. Depth of discharge is the amount of capacity that has been taken out of the battery. If we start with a battery that is 100% fully charged and we use 10% of the capacity of the battery, we say we've used a 10% depth of discharge. We've only used 10% of that battery capacity. If I use half the battery capacity, I'd say I used a 50% depth of discharge. If I'm going to use 80% of the capacity of the battery, I'd say I have an 80% depth of discharge. I will say depth of discharge is primarily used when designing systems. We very rarely use depth of discharge as a term when describing a system that is operating. When the system is operating, we typically refer to state of charge, or SOC, and that's how much capacity is remaining in the battery. So if I use 10% of the capacity of the battery, I still have a 90% state of charge. If I use half of the capacity of the battery, I have a 50% state of charge. If I use 80% of the capacity of the battery, I have a 20% state of charge. So depth of discharge and state of charge are inverse relation to each other. Days of autonomy is another term that we use when designing battery-based system, and this is how many days the battery or battery bank can go from fully charged to the maximum depth of discharge that we design the system for with no recharging during that time. On day one, if I start off with a fully charged battery, I've got no charging sources. If I can run loads with that battery before hitting my maximum depth of discharge, that's the number of days of autonomy. So say my maximum depth of discharge is 80%, and I can power the loads for 2 days before the battery goes from 100% state of charge to a 20% state of charge, which would be an 80% depth of discharge. If I can go 2 days, then I have 2 days of autonomy. If I can go 4 days, I have 4 days of autonomy. If I go half a day, it's a half a day of autonomy. Cycle life is the number of charge and discharge cycles that a battery can provide before it reaches the end of its useful life. A charge and a discharge cycle is usually seen as going from 100% state of charge to the maximum depth of discharge and then back to 100% state of charge. So that would be one cycle. If a battery can do 2,000 cycles and it's doing a cycle a day, then it's going to last for approximately 2,000 days. And there's going to be different metrics around cycle life depending on the chemistry of the battery that you're working with. Battery Management System, or BMS, is a system that manages the charging and discharging of the batteries to prevent damage to the cells internally in the battery. This is most commonly seen with lithium-ion batteries. They have very specific charging and discharging requirements, both for voltage and temperature. That battery management system is going to monitor the voltage of the cells, the temperature of the cells, the state of charge of the cells, and some other parameters as well that will vary depending on the manufacturer of the battery management system. Without that battery management system, we could overcharge or over-discharge those battery cells, which could cause damage to the cells and may even have a catastrophic effect like a fire or an explosion. Battery management systems will stop charging or discharging a lithium-ion battery cell if they are outside the operating parameters of that battery. So battery management systems, most common with lithium-ion batteries, and really every quality lithium-ion battery that we're using with renewable energy systems is going to come with a battery management system. Now that we've covered terms, let's look at some battery construction. Each battery has an anode. Doesn't matter what type of battery chemistry we're using, they all have an anode. That is the negative plate inside the cell. In this diagram, this is the thick black line. It also has a cathode, which is the positive plate inside the battery cell. It's the red thick line in this case. And there's a separator between the anode and the cathode that keeps those two plates separate. If they were to come into contact with each other, that would short circuit the battery cell, and that typically would cause a catastrophic failure in the battery, may cause a fire, may cause an explosion. This battery diagram that we're seeing here is multiple cells combined into a single case. We can see that the cell on the left is one cell, and there's 5 other cells contained with this in this battery for 6 cells total inside one solid case. In the battery, the cells are connected in series, which is going to build voltage. So if this was a lead acid battery, a typical nominal cell voltage is about 2 volts. If we combine 6 of them together, we will get a 12 volt nominal battery. Each battery has some type of electrolyte. The chemistry of the electrolyte will vary depending on the type of battery you're working with. And the electrolyte is really allowing the electrons to move between the anode and the cathode, and that is how the battery is able to charge or discharge. The type of material used for the anode and the cathode and the type of material used for the electrolyte is going to vary pretty dramatically between different types of batteries. You'll see different metals used for anodes and cathodes between lithium ion, lead acid, nickel iron batteries. Also, the electrolytes in these batteries will be different as well. On the end cells, on both the positive and the negative side, you'll have a connector coming out that will connect to the terminals on the battery, both the positive terminal and the negative terminal. Key points we need to think about in this lesson: batteries are used for storing energy so that we can have that energy available at a later time when we need it. They can also provide portable power to go to locations where the utility or other energy sources aren't available. And they can be used to do advanced functions like improving the power quality of the utility grid. There are many important terms that are used when describing and designing battery-based systems. DOD is depth of discharge, that's how much we've removed from the battery. SOC is state of charge, which is how much capacity is left in the battery. DOA is days of autonomy, that's how many days the battery can go from fully charged to our maximum depth of discharge without any charging sources. BMS is battery management system that protects and monitors the battery to make sure it's operating within its designed parameters. Cycle life is the amount of charge and discharge cycles we anticipate getting out of the battery before it reaches its end of life. Positive and negative terminals, we see those on the batteries, we see those in the plates inside an individual cell, and we also have the electrolyte, which is the conductive element inside the battery that allows electrons to flow between the anode and the cathode. That's the end of this introductory lesson on energy storage. I hope you enjoyed it and found some useful information, and we'll see you next time. Thank you very much.